Assalamu alaikum. Today I want to talk about chapter 14, part 3, chemical kinetics. Half-life. The half-life of a reaction is the time required for the concentration of a reactant to reach half its initial value, which means concentration of A at half time equal 0.5 the initial concentration of the reactant. Half-life is a convenient way to describe how fast reaction occurs, especially if it is a first-order process. A fast reaction has a short half-life. Half-life. We can determine the half-life of a first-order reaction by substituting concentration of A at T half into the equation, this one, and to get the final equation, then T1 half equal 0.693 K. This is what is important. Then if you know the rate constant, you can determine half-life. So this half-life does not depend on the concentration of reactant initially. However, for a zero-order process, the half-life is half-life equal concentration of A initially divided by 2K, which means for a zero-order reaction, the half-life depends on the initial concentration of reactant. Now, in this figure, this is kinetic data for the measurement of methyl isonitrile to acetonitrile at 199 degrees centigrade, showing the half-life of the reaction. You see here, in a first-order reaction, the concentration of the reactant decreases by 1/2 in each series of regularly spaced time intervals. Each time is T1/2. So here we have the first half-life occurs at around 13,600 seconds, whereas the second half-life occurs at around 27,200 seconds. So this is how you determine half-life. Now, let's look at this sample exercise determining the half-life of a first-order reaction. Now, the same data we saw in part 2, the reaction of butyl chloride with water is a first reaction order. First-order reaction, figure C, shows how the concentration of this changes with time at particular temperature. From that graph, estimate the half-life for this reaction and use the half-life for A to calculate the rate constant. Then, if we look here, a plan to estimate half-life, we can select the concentration and then determine the time required for the concentration to decrease to half of that value. So here, from the graph, we see that the initial value is 0.100 molar. The half-life of the first-order reaction is the time required for this concentration to decrease to 0.05, from 0.1 to 0.05, which the point occurs at approximately 340 seconds. And we can solve for K, and K equal this. So at the end of the second half-life, which should occur at twice this, 680 seconds, the concentration should have decreased by it another factor of 2, and that's 0.025 molar. Inspection of the graph shows this is indeed the case. You can also solve this practice exercise on the same plot. So this is the plot for that figure, concentration of butyl chloride as a function of time. Okay, so from this figure, this is initial concentration 0.1, and here we have concentration at the first half-life. If you put line here and then line here, then you will get this value, 340 seconds. For a second-order reaction, depends on the concentration of reactant. So after we calculate, the half-life for a second-order reaction equal 1 divided by K times the initial concentration of A naught. So both zero-order and second-order depend on the initial concentration of A. However, first-order reaction does not depend on the initial concentration of A. Now, temperature and rate. Generally, as temperature increases, so does the reaction rate. As you can see here, this is because K is temperature dependent. So K with temperature. as the temperature increases, so does the reaction rate. This is because K is temperature dependent. Now, this figure shows us temperature dependence of the rate constant for methyl isonitrile virgin to acetonitrile, and in this figure here, we have here high temperature and lower temperature. We can see temperature affects the rate of the chemiluminescence reaction in light sticks. This is called a light stick. You see, so at the higher temperature, we can see that the light sticks produce a brighter light here, a brighter light at higher temperature than at a lower temperature. Although the light stick glows more brightly initially, its luminescence also dies out more rapidly at higher temperature. So the rate constant, and hence the rate of the reaction, increase rapidly with temperature, approximately doubling for each rise. Now, the collagen theory: in a chemical reaction, bonds are broken and new bonds are formed. Molecules can only react if they collide with each other. The greater the number of collisions per second, the greater the reaction rate. As molecules move faster, they collide more forcefully with more energy and more frequently, increasing reaction rates. Furthermore, molecules must collide with the correct orientation, as you can see here, and with enough energy to cause bond breakage and bond formation. For example, the reaction between Cl plus NOCl to form NO plus Cl2. So Cl must come from the side of Cl in this molecule. In order, this is called correct orientation, and with enough energy, collision occurs. And then this is after collision, we have Cl2 plus NO. Now, in other words, there is a minimum energy required for a reaction. This is called the activation energy. Just as a ball cannot get over a hill if it does not roll up the hill, with enough energy, a reaction cannot occur unless the molecules possesses sufficient energy to get over the activation energy barrier, like this. Now, reaction coordinate diagrams. This figure shows us energy profile for conversion of methyl isonitrile into its isomer acetonitrile. Although this is at the beginning, low energy, this is energy of reactant. It's helpful to visualize energy changes throughout a process on a reaction coordinate diagram like this, one for the rearrangement of methyl isonitrile. So you see here rearrangement occurred, and then we reach here at the transition state or activated complex, and bond breaking start to occur, and then bond forming. So, and you can see here, this is the activation energy, which is the minimum energy required to initiate the reaction, and delta E is the energy, the free energy of the reaction, delta E, and it's equal energy of products minus energy of reactants. And you can see for this reaction, it is an exergonic reaction. Now, the molecule having the arrangement of atoms at the top of the barrier is called, either we call it the activated complex or we call it the transition state. So the conversion is exothermic, as I said, and the energy change for the reaction, delta E, has no effect on reaction rate, however. Now, the rate depends on the magnitude of E of A. Generally, the lower the value of EA is, the faster is the reaction. So, as we said, the high point on the diagram is the transition state or activated complex. The species present at the transition state is called the activated complex. Now, the energy gap between reactants and products, between the reactants and the activated complex, is the activation energy barrier. Again, the rate depends on the magnitude of E of A. Generally, the lower the value of EA, the faster is the reaction. Now we come to the so-called Maxwell-Boltzmann distributions. This figure shows us the effect of temperature on the distribution of kinetic energies of molecules in a sample. لاحظوا here in this figure we are comparing, we show the distribution of kinetic energy of molecules in a sample for two temperatures. Okay, now comparing them with the minimum energy needed for reaction, the E of A. Now, at the higher temperature here, at the higher temperature, a much greater fraction, as you can see here, a much greater fraction of the molecules have kinetic energy greater than E of A, so which leads to a greater rate of reaction. So temperature is defined as the measure of the average kinetic energy of the molecules in a sample. So at any temperature, there is a wide distribution of kinetic energies. Now, as the temperature increases, the curves flattens and broadens. Thus, at high temperatures, a larger population of molecules, as you can see here, has higher energy. Now, if the dotted line represents the activation energy, then as the temperature increases, so does the fraction of molecules that can overcome the activation energy barrier. So as a result, the reaction rate increases. Now, this fraction of molecules that have an energy equal to or greater than E of A is given by this expression. Okay, in this equation, R is the gas constant and T is the absolute temperature. Now, a calculated value of F at 310 Kelvin is equal 1.4 times 10 to the minus 17, which means thus a 10-degree increase in temperature produces a 3.6-fold increase in the fraction of molecules possessing at least 100 kilojoule per mole of energy. Now, Arrhenius equation. Seventh, Arrhenius developed a mathematical relationship between K, the rate constant, and activation energy, as you can see here, where A is the frequency factor, a number that represents the likelihood that collisions would occur with the proper orientation for reaction. As the magnitude of E of A increases, K decreases because the fraction of molecules that possesses the required energy is smaller. Thus, reaction rates decrease as activation energy increases. Now let's see this sample exercise relating energy profiles to activation energies and speed of reaction. Consider a series of reactions having the following energy profile. You see? Now rank the reactions from slowest to fastest if they have nearly the same frequency factors. So the lower the activation energy, the faster the reaction. So the value of delta E does not affect the rate, hence the order is, you see here, 2 is less than 3 and 3 is less than 1. So this is the activation energy, you see, 25, 20, 15. So the smaller the value of activation energy, as you can see, the faster the reaction. As you can see here, this is the arrangement. So 2, the 25, is less than 3 and 3 is less than 1. Imagine that these reactions are reversed. Rank these reverse reactions from slowest to fastest. Then here, first we rank them from slowest to fastest. So fastest is number 1 because it has the lowest activation energy. Then we have 3 with 20 kilojoule per mole. Then 1. This one is the all in all from slowest to fastest. So 2 here is less than 3 and 3 is less than 1. So the fastest is 1 and the slowest is 2. Here the opposite. We want to arrange them in the order of slowest to fastest. 2 is less than 1, 1 is less than 3, because activation energy values are 40, 25 and 15 kilojoule respectively, if we reverse the reaction. Okay. Now, determining the activation energy. Taking the natural log of both sides, the equation becomes this. And it is an equation of a straight line. When we plot length k versus 1 over t, we get a straight line with the slope equal minus E of A divided by R, and then B here we have the y-intercept equal ln K. Therefore, if K is determined experimentally at several temperatures, E of A can be calculated from the slope of the plot of ln K versus 1 over T, determining the energy of activation. Now, if we have the following data for the rearrangement of methyl isonitrile, we have temperature and K. You see, from these data, calculate the activation energy for the reaction. What is the value of the rate constant at the temperature 430 K? So here we can obtain activation energy from the slope of the graph of ln K versus 1 over T. So we must also convert these into absolute temperature and then take ln K also and make a plot, and from the slope of the graph of ln K versus 1 over T and the rate constant K at a particular temperature. Once we know activation energy, we can use this equation together with the given rate data to calculate rate constant at 430. So this is the equation. Ln K1 divided by K2 equal activation energy divided by R times 1 over T2 minus 1 over T1. So as I told you, we converted the temperature into absolute, and then we take 1 over T and then ln K. Then we plot ln K versus 1 over T, and we get a graph of ln K versus 1 over T is a straight line as shown here, as you can see. So this is a graphical determination of activation energy. The natural log of the rate constant for the rearrangement of methyl isonitrile is plotted as a function of 1 over T. The linear relationship is predicted by the Arrhenius equation, giving a slope of, so the slope of this line equal minus activation energy divided by R. Let's see. So the slope equal delta y divided by delta x, and we can get it from the slope. Now slope equal minus E of A divided by R. And then we can determine activation energy. R is the constant, and then we get this 160 kilojoule per mole. This is the activation energy. Now we report the activation energy to only two significant figures because we are limited by the precision with which we can read the graph in this figure. Now to determine the rate constant K1 at T1 430K, we can use the previous equation, this one, with activation energy 160 mole and one of the rate constants and temperature from the given data, such as if we take the value of K2 and T2. So we apply it here. Ln K1, we want to determine K1 divided by K2, this is K2. This equal activation energy, the one we determined, divided by R, this is R, constant, times 1 over T2, 1 over T minus 1 over T1. And we must convert the kilojoule into joule, and we get this value for K1. Then K1 equal 1 times 10 to the minus 6 per second. Note that the units of K1 are the same as those of K2. Thank you. End of part 3.